Hey, how's it going? My name is Sean Hoffman, and for my third and final project here, I'm going to continue on what I started on with my last project regarding utilizing AI and machine learning for ensuring uptime in mission critical environments like hyperscale data centers or validated life science facilities where they're developing pharmaceuticals in critical environments where redundancy and ensuring power system uptime is critical and a huge factor for the solution that we're providing to our customer. I think if we integrate AI and machine learning into this concept, we could definitely provide a better and more improved solution to our customer. I already kind of did the introduction. My name is Sean Hoffman again, and here we go. So as a project overview, we're going to cover mostly mission critical environments, but I'm also might touch on validated life science facilities as well. So the focus here is on data centers, validated life science sites requiring high reliability and minimal downtime. Predictive maintenance dashboard. So a dashboard will proactively identify proactively identifies potential system failures before they occur to ensure power uptime. So this could be anything from power analytics or something of that magnitude. But yeah, this presentation explores the application of artificial intelligence to ensure system uptime in mission critical environments, specifically focused on data centers and the validated life science sites. These environments demand high reliability and minimal downtime due to their operational and regulatory importance. The goal is to develop a predictive maintenance dashboard that proactively identifies potential system failures before they occur. We were planning on, leveraging machine learning models trained on historical sensor data and operational logs. The solution here aims to reduce manual checks, improve reliability, and support compliance with the industry standards. The dashboard will provide actionable insights to operators, enabling timely interventions and enhancing overall system resilience. Task analysis. So next, we're going to go into understanding the problem and task flow. In a mission critical environment, such as data centers and validated life science sites, unplanned downtime can lead to significant financial losses for our customers, regulatory noncompliance, and operational disruptions. The key task is to predict anomalies and potential failures before they occur. Currently, operators rely on manual checks, reactive alarm systems, which are not sufficient for proactive maintenance. A task analysis will reveals that the workflow involves monitoring sensor data, interpreting logs, and scheduling maintenance based on observed issues. Machine learning can simplify this task flow by automating anomaly detection, providing predictive insights. This reduces cognitive load on operators and enables more efficient resource allocation for the customer. The insights from task analysis suggest that integrating AI into existing workflow can enhance reliability and streamline operations. User experience design, designing the interaction model. The user experience design for the AI solution centers around a dashboard integrated with the building management system. Users interact with the system by uploading sensor data, accessing real-time analytics. Some key considerations include user inputs, feedback loops, transparency, and communication of uncertainty. Inputs consist of environmental and operational data from sensors and logs. The feedback loop involves the model flagging high-risk equipment and suggesting maintenance actions. Transparency is achieved by displaying confidence scores and highlighting the features that influence predictions. Uncertainty is communicated through color-coded risk levels, helping users prioritize actions. This design ensures that the AI system is intuitive, informative, and supportive of user decision making in high stakes environments, such as, you know, uh, Category 4 mission critical data centers, as well as validated life science facilities. Privacy considerations in these type of critical environments include um, privacy considerations are paramount in mission critical data centers and validated life science sites due to the sensitivity of operational data. This includes IP addresses, backnet configurations, control logs, and validation records. Regulatory compliance is essential with GDPR and CCPA applicable for personal data, and HIPAA relevant in life science when patient-related data is involved. That's not always the case in life science, but sometimes in healthcare, hospitals, and also other life science facilities, there's like a slight crossover between the two. Anytime there'll be personal data involved, that's where HIPAA will become relevant. Additionally, FDA is a huge part of the life science validated space. 21 CFR Part 11 mandates strict controls over electronic records in validated environments. This is to protect data. Encryption must be applied both at rest and in transit. Access should be role-based. Um, Anonymization techniques should be used where feasible. Privacy by design principles should guide system architecture, ensuring that the data protection is embedded from the outset. These measures help maintain trust and compliance while enabling effective AI deployments. Ethical considerations, ensuring fairness and accountability. Ethical considerations in AI deployment for mission critical environments include addressing bias, ensuring fairness, maintaining accountability, and promoting transparency. Bias can arise if models are trained in limited facility types, leading to poor generalization. Representation bias is particularly concerning in the validated life science sites where regulatory compliance is critical. Fairness requires that the model provides equal reliability across all systems, not just high value assets. Accountability involves keeping a human in the loop for final decisions, especially in validated environments or mission critical data center environments. Transparency is achieved by explaining predictions through feature importance and confidence scores. Ethical risk migration strategies include data sheets for data sets, applying ethical checklists, and conducting ethical pre-mortems. These practices ensure that AI systems are fair, accountable, and transparent, aligning with industry standards and societal expectations. Human and societal considerations. So we have human and societal considerations focus on augmenting human capabilities rather than replacing them. Building trust in AI systems and managing change effectively. In mission critical environments, operators must trust the AI system to make informed decisions. Trust is built by communicating model performance, presenting confidence scores, providing explanations, and acknowledging limitations. Human in the loop mechanisms ensure quality control and allow for corrective actions. Change management is essential for adoption, involving proactive user education, clear communication of value, and addressing concerns. A step by step deployment roadmap with early adopters and training programs can facilitate smooth integration. Monitoring adoption and usage helps identify areas for improvement. These strategies ensure that AI systems are accepted and effectively used in high stakes environments. Here just like a brief screenshot and breakdown of what the predictive maintenance dashboard would look like. The demo showcases a predictive maintenance dashboard designed for specifically for designed for mission critical data centers and validated life science sites. The dashboard displays a list of equipment with associated risk levels, suggested maintenance dates, and confidence scores. It integrates real-time sensor data and historical logs to provide actionable insights. Color-coded indicators help users quickly identify high-risk assets, while detailed explanations support decision making. The dashboard is designed to be intuitive and informative, aligning with user workflows and regulatory requirements. This visual representation of the AI model's output demonstrates its practical application and effectiveness in preventing downtime and ensuring compliance.